Okay. I have realized from the exam that you have some problem with integration. This is why I included this problem for you. Okay. So a liquid of density rho flows through a 90 degrees band as shown in the figure and issues vertically from a uniformly porous section of length L. Neglecting the weight, find a result for the support torque M required to be applied at point O. So here you have a distributed flux, okay, at this section. And you want to predict what should be the torque TO applied at O to hold your system at rest, okay? So again, we are in steady operations. So you have that in this problem, the inlet is from this side. So this is m dot Vn vector. This vector is passing by O, so it cannot produce a moment about O. So the rate of angular momentum for the inlet flux is 0. So just you have to compute what is the angular momentum rate at the outlet. Okay. Now, what is little bit challenging for this outlet, that you should perform integration to get your total momentum flux. Why? Because here, whenever you have something that is varying, so when you go over this section, the distance from O is not constant. Okay. So if you want to compute the moment, you should do an integral procedure, because for each small element of your flow, you have that the distance to O is different. So you can say, because I am having variation in distance, let me express let me do an integral procedure to find the total angular momentum. Okay. So how to do this? First, if I want to calculate first the flow rate, okay, they told me in the problem that I have the liquid is of density rho. They gave me the density of the liquid. They gave me the length L of the porous section. Okay, and they told me that I have the velocity, the exiting velocity is VW. Okay, so if I want to compute my total flow rate, I should here perform an integral procedure, okay, over my, because this flow is over the circle, okay, it's over the whole circumference, okay, because you have a porous section. If you want here, it's turning 360 degrees. So the total flow rate that is exiting my porous section can be computed by integration, okay, as integral from 0 to L, because the length is varying from 0 to L here, okay, of for each circumference, okay, what is the elementary area? You know that to calculate Q, you should do integral. The formula is integral V dA. Okay. Now, what is the elementary area you can take here? The elementary area dA you can take here is pi d, okay, which is the perimeter of the circle, times an elementary thickness dx. Okay. هلا in this problem كان فينا ما نعمل integration. You know why? Because V at the exit is constant. But I will do for you integral procedure in case V is not constant, to know what to do. And if, for example, if they gave you a profile of velocity that is linear here, so V is varying in a linear way with X, then you should perform integral procedure to find the total flow rate. Okay. So this is why, to be familiar with the integration, all you have to do is to think what is my variable here. My variable is X. So as I move along X, I have change in velocity. Then I should express at each X what is the velocity value. So here, for example, if I give you a straight line, you get v function of X, and you replace in this relation. If I give you v constant, so here you will see that no need for integration, because all parameters here will be constant, since you have v constant and pi d constant. You can take them outside of the integral, and then you get that your total flow rate will be vw times pi d times the total length f. So here you could have done this without integration because v is uniform. But if v is function of x, all you have to do is to perform the integral procedure. You say what is the variable is x because v is changing with x. So I should find v function of x, and then I perform my integral. Okay. So this is first how we get the flow rate, and by multiplying by rho, we can get the mass flow rate m dot. Okay. Now, the next step is to compute the angular momentum rate at the outlet. Here, I should perform integration. Okay. Why? Because the distance to O is varying. So each elementary force dF, okay, or here, if you want, what I am getting, not the moment of a force, I'm getting the moment of linear momentum, m dot v, rate of linear momentum, m dot v. So when I want to perform my calculation, okay, I should do integral procedure. So I will apply the formula that the rate of angular momentum al control surface is integral over the control surface of r vectorial v times dm dot, elementary mass flow rate. Okay. Now for each elementary mass flow rate that is exiting my system, it is characterized by a certain distance from O, and this distance is varying. This distance is varying from what to what? It's varying from r. At this point, the distance from O is equal to r. And at the final point, it's equal to r plus L. So I can say that I can consider a variable x, okay, between, for any value in between these two, I can consider that the distance from O to this point is equal to r plus x, and then x is varying to cover the whole surface. X should vary from 0 to L. So now I can write that r vectorial v can be replaced by the following. R is r plus x. For any element, here v is constant. So for any point I consider, I have the same velocity vw. So while what is varying is just the distance to O. So in general, for any section x, I have the distance is r plus x, the velocity is vw, and m dot out, the elementary dm dot out, is equal to rho times vw times dA. And what is the elementary area dA? dA is, since I'm considering a small thickness dx, okay, the elementary area dA is dx times pi times d. Okay, so I end up with the following result. I'm integrating from 0 to L. Now concerning the direction, here no need to do vectorial product. You can do it. If you do the vectorial product, r vector is along I, and v vector is along k, I vectorial k, j, if we consider this as y-axis, I vectorial j will give you positive k. Or if you want, because it's a 2D application, you can say just I will do the right-hand rule. So the moment of this vector about O is counterclockwise, so it's positive. Okay. So both results will tell you that your angular momentum flux is rate is along k. So you can write now that you have integral from 0 to L of r plus x VW times rho times pi d VW. So this is m dot. This term is this term will give you the elementary mass flow rate dm dot, which is equal to rho times v times dA. Okay, and now all you have to do is to perform your integration. Here VW is constant. If it was function of x, all you have to do is to plot here, replace VW by its x function, and you integrate. So now since you have constant parameters, you take them outside of the integral, and you just integrate the variable parameter, which is this one. Okay, the integral of r plus x with respect to x is r plus x squared over 2, and then you apply your integration between 0 and L, and you get your result. Okay, so this will give you that the torque that should be applied should be equal to rho q VW times r plus L over, and you will be done. Okay, any question on this problem? Okay. A final problem on angular momentum. You have a rotating dishwasher arm delivers at 40 degrees to 6 nozzles as shown in the following figure. The total flow rate is 3 gal per minute, and each nozzle has a diameter of 3/16 inch. If the nozzle flows are equal and friction is negligible, estimate the steady rotation rate of the arm in revolution per minute. Okay, so you want to determine what is the value of omega. So under the effect of the jet, as you are getting the jet out, okay, you will have this will cause rotation of your arm, and this direction of rotation will be opposite to the direction of jet exit. To understand this more, it's like the effect in rockets. In rockets, when you do expulsion of gases to the backward, this will drive your rocket upward. Here also, as you are exiting a jet, and the exiting jet is, as you can see, is tending to create a counterclockwise moment, this will lead to clockwise rotation of your system. So the question is, in steady condition, what will be the value of omega? Okay, this is the question. So since we are in a problem of rotation, so you can think about the angular momentum principle to be able to get the value of omega. Okay, now this is, you have here two views of your system. This is the view in XY plane, and if I do a cross section like this, if I do a cut, this is what I see. Okay, this will give you the direction of your velocity vector. So your velocity vector, as you can see here, can be decomposed into two components. One that is parallel to the axis of rotation. Okay, so if you want, in this figure, this is the axis of rotation. This is Z. Okay, and this direction is Y. Okay, so here you are observing plane YZ. Okay, while in this case you are observing plane XY. Okay, now why they gave us this figure? Because the velocity vector is not in the y-axis plane. It can be decomposed into two components, one along y which is equal to V cosine 40, and one along Z, which is equal to V sine 40, okay? But of course, you know that when I consider angular momentum, the component parallel to the axis of rotation will not produce any effect. So when I perform angular momentum calculation, I will just consider the component V cosine 40 that is perpendicular to the axis of rotation, okay? So all of these components here are equal to V cosine 40 in relative. This is the relative velocity between the jet and the system, okay? So you can say that V relative along Y is equal to V cosine 40, okay? Now let us read the given to know exactly what they gave us. They told us that we have 6 nozzles, and the flow rate, the total flow rate, Q total, is 3 gal per minute, okay? And so first we can convert to the unit of feet cube per second. This will give us Q in English units. And then to get m dot, okay, we multiply by rho. Now, since they told us that the flow is equally distributed between the 6 nozzles, so for each one, okay, for each nozzle, what is m dot? For each nozzle, m dot is rho Q over 6, okay? So you can calculate m dot for the different nozzles in slug per second. And now, also, you are interested into the velocity delivered for each nozzle. So V for each nozzle is Q over A. Q, of course, for each one, which is Q over 6, Q total over 6, over the area of each nozzle. Now, for each nozzle, the diameter is 3 over 16 inch. So please pay attention for units. When you have inch to convert to feet, just you have to divide by 12. This is why they divided by 12 here. And here they divided by 448.8 in order to convert units from gal per minute to feet cube per second. Okay? So now you have the velocity. Please pay attention when they give you a flow rate and you calculate V. V that you calculate is the relative velocity between the system and the nozzle, because we said that when we talk about m dot, we consider the relative velocity involved between the control surface and system, okay? Because if you have your control volume moving, and this is the case here, you have rotation, okay? So your arm is rotating. Since the arm is rotating, what will happen is that the velocity at a point here will be the combination of the relative velocity, which I can get from m dot, and the velocity of rotation. So if I have a velocity omega here, okay, this rotation will give to any point a velocity equal to, so for example, at this point, I have a velocity equal to omega times r. R is the distance between O and this point. Okay, so I should then pay attention that for each point I have the V relative, which is due to m dot calculated, and I have the velocity of rotation. And now you know that when I apply angular momentum principle, for the angular momentum principle, I take a control volume that is fixed, okay, and just is where my bar that is rotating is inside the control volume, okay? So since my control volume is fixed, when I apply the angular momentum principle, I will use absolute velocities for V. So please don't confuse two things. You have the rod system is rotating, okay? But the control volume that is enclosing it is fixed. So at this instant, at any instant, the control volume considered is just a fixed control volume crossing the inlets and outlets of your rotating system. Okay, so this is why when you apply angular momentum principle, you will use absolute velocities in your system. Okay, this is why to find the absolute velocity at any outlet of the nozzle, I should do V relative minus V relative at this nozzle, so I call it V relative I, and we have seen that V relative is the same everywhere in magnitude, minus omega times Ri. Okay, so now in order to find what is the angular velocity, I should write the principle of angular momentum for my system. Okay, so the angular momentum theorem applied to my system about O will give me the following. Sum of moments about O equals to the total torque about O. But here, if you go to the given, they said there is no friction. No friction, and I don't have any if you have here, I have a support at O, so forces are applied at O, cannot do any moments about O. And so I can say in this case that no external moments about O. So sum of moments about O is equal to 0. And this should be equal to the rate of angular momentum fluxes crossing the control surface of my system. And we said that the control surface is enclosing the rotating arm and it's crossing in the outlets. Okay, so as you can see here, I just have to consider fluxes. Concerning the inlet is from the in this problem I have the dishwasher, okay, is providing water perpendicular to the perpendicular to this plane, so it's along the axis of rotation. This is why for the inlet flux I don't have an angular momentum, so m dot nvn is 0. This term will cancel out. I will just have the angular momentum fluxes on the 6 outlets, so I should do summation over the outlets of mi times Ri vectorial Vi. And as I told you, this is the absolute velocity. I will take an absolute velocity. The absolute velocity is computed as V relative plus V rotation. Okay. And since they are opposite, because if you look at your figure, at any, if you consider the parts here to the right, their velocities are upward, relative velocities, but since rotation is clockwise, okay, so I will have rotation velocities downward. So when I do the additions, they will be opposite. And here from this side, same, because due to rotation, from this side velocity will be up, while V relative are down. So for both cases, I have the, if you want, I have subtraction between the magnitude of VI cosine 40 and omega RR. And now you can see that all of outlets are producing moment about all the angular momentum of their fluxes are counterclockwise. Okay, this is why I will put it's equal to plus m dot. So now just I should pay attention for each flux to multiply by the corresponding distance. Okay, if you look here, you can pay attention that I have like couples. So because these two, due to symmetry, these two fluxes are equidistant from O, so they will create a couple. So if you want, the total moment will be equal to m dot VI, m dot I VI times what first? Times this distance, which is 5 times 2. Okay. Plus, I should add the angular momentum rate created by this couple. So 5 with 2. 5 with 2, you have same m dot VI, same value of m dot VI. But what is different is the distance. So now the distance is this whole one, which is 11 times 2, which is 22. Okay. And finally, you have the final couple, 6 and 1. The total distance is, you have 5 plus 6 plus 5, 16 times 2, 32. So in total, if you want, it's m dot I times VI absolute, and VI absolute is VI cosine 40 minus omega RI. Here, look, here I should pay attention. RI is varying, so I cannot take it into factor, okay? Because when you take the first couple, what is RI for the first couple? For the first couple, RI is 5. For the second couple, RI is 5 plus 6, 11. And for the last couple, RI is 5 plus 6 plus 5, which is 16. Okay, so you can do this problem in several ways. You can take for each one, and for example, you take this m dot, you say it's m dot VI cosine 40 minus omega times RI for this part here, 5 over, because it's in inch, I should convert to feet, so times 5 over 12. Okay, now since these two, if you do this alone and you do this alone, you will get the same result, لأنهم equal in magnitude وعندهم same distance from O. Okay, لأنه ال RI is same for both. This is why I told you فيكم كل الاثنين تاخذون مع بعض ككابل، لأنه if you take each one alone حيطلع لكم نفس الريزلت واثنيناتهم عم يعطوكم counter clockwise moment. So if you want, you can group them 2 by 2. Okay, يعني عندي 2 times m dot VI cosine 40 omega times 5 over 12 times RI اللي هي times 5. اوكي، ما هي 2 times 5 بيطلع لكم الديستنس بيناتهم اللي هي 10، اللي كانه اخذته كابل. اوكي، او بتعملوا لهول كل وحده لحالها وبتقولوا انهم equal، فيكم دغري تحطوا 2 times، او بتاخذوهم ككابل، بدل ما تضربوا بديستنس لكل وحده 5 دغري بتضربوا بتوتال ديستنس بيناتهم 10. And you will repeat the same work for ال 5 مع 2. التوتال ديستنس بيناتهم as we said ال RI لكل وحده منهم هي 5 plus 6، وقتها بدكم تعملوا replacement بالفي تبعهم بدكم تحطوا مطرح RI 5 plus 6 بيطلع لكم 11. اوكي، بترجعوا بتعملوا الكابل يلي بيخلقوه الديستنس بيناتهم هي 22، او بتاخذوا كل وحده لحالها، بتاخذوا times 11 بس تطلع times 2 لانه it is repeated 2 times، it's equivalent to 22. Okay, and finally for the couple 6 1, when you replace RI here, you should replace by 5 plus 6 plus 5, اللي هي 16, and or you account 2 times for the term, or you just multiply m dot v total by the distance between 1 and 6, اللي هي 16 times 2, 30. Okay. Any question on this? So now, all you have to do then is to write that this is equal to 0, since sum of moment about O is 0. Since I don't have friction and I don't have any couple or any force-producing moment about O, this equation will give you the value of omega. The only unknown in this equation is omega. So you can calculate what will be the velocity of rotation in this case. Okay, and don't forget, you got it in radians per second, and since they asked for revolution per minute, so you just have to convert. Okay, to do this, you divide by 2p, and you divide and you multiply by 60. Okay, because to go from radian to revolution, we divide by 2 pi, and to go from per second to per minute, we multiply by 60. Any question on this? Okay, so we are done with angular momentum problems. Hopefully next time we'll start a new chapter. Bye.